The Baire Category Theorem has three equivalent forms, three different ways of saying the same powerful truth about complete metric spaces. Statement 1. Every complete metric space is of second category as a subset of itself. In plain terms, a complete space has too much substance to be exhausted by countably many thin, scattered sets. Statement 2. If a complete metric space is the union of a sequence of its subsets, then the closure of at least one set in the sequence must have a non-empty interior. Simply, if you cover a complete space with countably many pieces, at least one piece must be fat, its closure must contain a whole open ball somewhere inside it. Statement 3. If A1, A2, A3, and so on, are nowhere dense sets in a complete metric space X, then there exists a point in X that belongs to none of the ANS. In short, thin sets, no matter how many you stack, can never cover a complete space. There is always a point they miss. All three say the same thing: completeness is a shield against thinness. To understand these statements, for ideas matter. A set is nowhere dense if its closure has empty interior, it is scattered, with no open ball fitting inside anywhere. The interior of a set is the largest open set contained within it. The closure of a set is the set together with all its limit points. And a metric space is complete if every Cauchy sequence, every sequence whose terms grow arbitrarily close, converges to a point actually inside the space. Now the proof of statement 3, which implies the other two. Let A1, A2, A3 be nowhere dense sets in a complete metric space X. We will construct nested closed balls, each avoiding the corresponding set. Pick any open ball B in X. Since A1 is nowhere dense, its closure has empty interior, so B contains points outside the closure of A1. We find a closed ball B1, with radius less than 1/2, sitting inside B and completely outside the closure of A1. Repeat with B1 and A2. A2 is nowhere dense, so B1 contains points outside the closure of A2. Find a closed ball B2, radius less than 1/4, inside B1, and outside the closure of A2. By induction, at step n, we find a closed ball Bn with radius less than 1/2 to the n, nested inside the previous ball, and outside the closure of An. The radii go to 0. The centers form a Cauchy sequence. By completeness, the centers converge to some point x star inside X. Since x star is the limit of the centers from step n onward, it lies in every Bn. Each Bn is outside the closure of An. So x star does not belong to any An. There is our point. The complete space cannot be covered. Proved.